Hey everybody, I'm here at the home lab trying to work on this design for a cause thing. It's a Saturday morning. Birds are chirping out the window here. It's too early, but I've got my coffee. So I think we're ready to go here. Today, I had to bring some lab equipment home with me to get this portion of the build done. But we're going to talk about the moisture sensor. So here we are. Had to bring home an oscilloscope and a power supply to use. But what we're going to do is talk about these today. I briefly discussed them previously. I've used these before, and they worked great until this, and it's not even corrosion. I don't know. You can see there's a little bit of corrosion up here. Some copper got wet or something. Maybe it scratched through. I'm not sure. But this brown and blackness, this is actually soil buildup, sediment that has formed a layer over it. And this is why the project that was using it failed. So you can see this one's much worse. It ate off all the screen printing and the coating. But when this film built up over it, it changed the conductivity of it and it quit working. The controller thought that the soil dried out and it just pumped all the water out, bled the reservoir dry, and then the plant dried out after all the water was gone. So I want to look at a better version. I clean these up and they'll still work, no problem. But I don't think they have a good longevity aspect depending on what types of soils you have to work with. So I'm going to experiment. So if we look closely here, this little SOT23 package is just a transistor. And then we have a couple resistors. If we sit there and we trace out, which you can see the pathways, but we could probe it, find the continuity where everything goes. It's a really simple setup. There's nothing too fancy about it. All it does is as moisture builds up between these two terminals, electricity will start to flow. And then it allows a little bit of the current from the high side of the transistor to flow through here to here and to the base of this BJT. And that little bit of current is enough to turn the transistor on and allow the current to flow through it, which comes through here. So one of these resistors is either a pull-up or a pull-down resistor for the emitter. I mean, not the emitter, the base. And then the other one, which I haven't checked it, is either on the high side, on the collector, or on the emitter, just to limit current flow and create a voltage division for your microprocessor to read. It's really simple, and it works very effectively. So what I have done, got my TO92 package here. It's just a 3904 transistor, nothing fancy. And then I've got a resistor. And I only got one. This was just a random resistor. I just pulled it off out of the mix bin in the lab. So, I could fine tune this, but just for testing, this worked really well. So I've got some jumpers here. I've tried this in multiple configurations. I think I'm going to leave it right here. We'll kind of discuss why. But this middle one is the base, this is the collector, and this is the emitter. So top, bottom, and control. So all I'm going to do is nails. We're trying to make this stupid, simple, and cheap. I'm going to connect these, and these are going to be the probes. Is what will go in it. Now, I've got a more permanent idea because you can already see the surface rust on these. The corrosion will build up. And I'm going to end up with something like what happened here, because once this rust builds up, the conductivity of it will change. So what I also have here, this right here, thanks to being at the school, we got all kinds of stuff at our disposal. It's just a stainless steel rod. It's about 1/4 inch. And I just hacked off some pieces with some really messed up bolt cutters here. You can see it all damaged up. But my thought process is this isn't going to corrode like anything else will. This is supposed to be gold plated, but you see what happened to it? Well, stainless steel is naturally antimicrobial. Bacteria doesn't like to grow on it, and I think that might be enough to stop this sediment from building up on these. But stainless steel is a little bit harder to come by in developing areas of the world. So, I'm going to try and source out something. I may be able to find like just some stainless steel nails or screws to go as part of my little kit for rapid deployment. So I'm going to set it up, and then we'll do some testing. We've got the power supply, the oscilloscope. We'll see how things go. All right, so I went and connected everything. We're going to go through it real quick. So I've got my power supply connection here. We're set at 5 volts because we are going to use the Arduino's 5-volt power supply to drive this, because the goal is very low current. So the Arduino should be able to handle it. So if we follow our connections, I've just got my 5 volts connected to the collector. I've got my ground connected to the bottom side of the resistor, which is connected to the emitter. Then, also from the 5 volts, I'm going here through this jumper wire to this nail. And then coming off of my base, I've got this jumper wire which goes to the other nail. All right. And then my oscilloscope, my probe A, is connected to the top side of the resistor. So what I'm going to be doing is measuring the voltage across this resistor. And if we look here, nothing. 0 volts. Nothing's going on. All right. So I'm going to try and set this up to where we can watch everything all at once. All right. So here we go. I've got my 2 leads. And just what, you see that? That's just from me touching it. You can see I'm jumping up to like 0.5 volt just by it resting on my skin. The oils in my skin are enough conductivity for this. And now, if we think about it, my body has a resistance of about 3 mega ohms, 4 mega ohms, depending on how much I've had to drink. This resistor looks to be about 1200 ohms. It's not huge, it's a very small one. So I could change this balance by varying this and knowing what my soil resistance is. So if I look at this, there, if I get to the very tips of my fingertips, where they're the most sensitive, I got the most nerve endings, I make a good transfer. I'm getting up to, oh, actually, no, wait, we're at 2 volts per division. Apologies. So I'm getting just over 2 volts now. At the just resting phase where we were at earlier, I was getting about 1 volt. But you can see, as the resistivity changes of my body, I get a different voltage output. So if I moisten my fingers, wet them, and then do it, bam, I'm all the way up to 4 volts now, because I reduced my connectivity, which means the resistance from here to here has dropped compared to this, so you get a higher voltage. This is simple voltage divider stuff based on Kirchhoff's voltage law. Very simple things. And so I should be able to go get a plant, and that's what I'm about to do, and then we'll plug this in and see what happens. One thing I wanted to do real quick is show you why I like this setup. So if we look right now, I've got this 0 volts here. What I'm going to do is I'm going to look here on my power supply. I'm going to switch over to current draw. I'm currently not drawing any power from this. This is good for a low power system, but something it's kind of a catch-22. When I do this and I get full connectivity, I just crossed them. You can see I get a little bit of current draw. But that's where this resistor comes in. It not only does it create the voltage divider, but it also acts as a current limiting resistor. So if I put 5 full volts across this, I can use Ohm's law to find out how much current draw I'm going to have. And currently, I'm at 1 milliamp-ish. These meters on power supplies like this, they're not that accurate compared to a actual functioning digital multimeter or an ammeter. but it gives us a good ballpark. So 1 milliamp, and if you think about it, this is in moist conditions, so hopefully the majority of the time, that means I'm going to have a constant 1 milliamp draw. That's stuff we have to take into account when we plan our power consumption. I went and I grabbed one of my little seedling trays. I've got broccoli and some cauliflower here. Little seedlings started up, they're growing. As you can see, the soil's a little dry right now because, well, it's morning and I haven't watered them yet. But we're about to do some checking here. So what I'm going to do, so we're not connected to anything. We've got a low signal. Put that in there and then put that in there. So you see we got something. There is some conductive material in there. The soil is naturally conductive, but I'm sitting here around about 2 volts, middle of the road, and I would consider this fairly dry. So I'm going to add some water and we're going to see what happens here. I'm probably going to make a little mess. Always be careful when you're working with electricity and water because of its conductivity, but we're at such a low voltage and current, I don't have to worry about being electrocuted, but I have to worry about damage to expensive equipment. So I'm going to add just a little bit of water. This may take some time because the water is going to have to absorb and distribute through the soil. All right, you can see we've already moved up a little bit. Did you see that little jump? Now we're up to about an average of 3.5 volts, and it's climbing a little bit more. We're getting up to we're up to about 3 volts. We were at about 2.5. As the moisture moves to the soil, you can see the soil is darker here. That's because the water is soaking through it. And we've only put it in this one. Moving up, we're getting a little bit closer to 4 volts. So the thing is, we won't get that full 5 volts because the mineral content of the soil is always going to create some resistance. But once this soil is fully saturated, it should get pretty close to a short circuit. And that's what we're wanting. We want as much voltage across this as possible. And if we look over here, I'm not getting any current reading here. We're in microamps still, which is very good for our battery aspect or remote powering. But we're sitting here at just below 4 volts. Given enough time, once the soil got fully saturated, we could get really close. We'd probably get a solid 4 volts. But this shows us what our voltage range will be, and it'll help with programming. If we know what our max voltage and our base voltage is going to be, we can calibrate to get a more high resolution read. So if I then go, look at that, from one section to the next, I get nothing because the plastic of this tray is a perfect insulator. In this case, so I go back to this one right here. This one's drier. We've had more draw on it, and you can see that I'm down to about 1.2 volts ish. Here we can zoom in. So 1.3, 1.4 volts, but there's still a lot of noise in there. And you see, I'll become a cleaner circuit and that noise goes away. But when I leave it just there, now I'm at, about 1 volt. So if we go back to check here, so 1, 2, and we are banging all through the 2 volt range. It's just a lot of noise. If I move in closer to the plant, you can see we can get higher. We get closer to 3. The shorter the distance between the probes, the higher my voltage. We're all the way up there at 4 volts now. If I turn my division back down, yeah, we're sitting right on the 4 volt line. But I'm really close to this plant. I'm only measuring a small area, very small area. We're talking about this far apart. So I'm only measuring this much of the soil. We kind of want a further distance away because now we're reading the soil from here to here. We've got a range of this far. We see how much moisture it's holding in that whole gap. but we also have to be careful. We probably have to adjust our current limiting resistor over here. See, just me touching it dampens. I add some capacitance in there to take that noise out. Amazing little things right there. Honestly, to get a better read from the Arduino, this is good knowledge. I may need to put a small capacitor in parallel with this resistor to get a smoother signal. That way my software is not jumping all over the place and like water, no water, water, no water, water. We want it to stay smooth and just run continuously until it gets to a point and then turn off. So that's currently where we're at. The next thing to do, test these stainless steel rods, because, you know, I don't know about you, but I haven't heard of stainless steel used in any electrical connections. So let's check those. Look at that. We got a reaction there. And actually, you see there's no noise in there. I'm willing to take a bet. I haven't done any research on this, but some of that noise may have came because of this little bit of current that I had on there and the moisture in here. Electrolysis. We were actually plating this with minerals in there, and that's probably where some of that noise was coming, was feedback from that process. With this being stainless steel, it's less, or it's more resistive to those type reactions. That's the whole point of stainless steel, is that it won't corrode. Oxidation and stuff like that are less likely, so we're not getting any feedback from it. Now, if we increase the voltage and push more current through there, we could get a better reading. But you can see we're sitting really low. I would like to see a much higher number. We're only about 1 volt there. Can we increase that voltage by adding water? All right, you can see we're already up to 2 volts. This is getting really saturated now. But you can see we didn't get that high. The stainless steel probes work. They just don't seem to conduct quite as well. And that probably comes down to the properties of the chromium iron mixture that makes it up. But we can see it would work. I don't know how well it'll work for longevity aspect, but it's something to play with. That's it for the moisture sensor. All we need for it is to do some coding. And that's one of the steps coming up in the future.